Hi everybody. I wanted to take a minute and go through a video example here of how to do a problem involving sex-linked genes. This comes out of our textbook, problem 5.10. This is just one of many examples in the chapter that are going to be really good practice for you to look at. So this problem sets us up with an explanation. A man who is colorblind with type O blood has children with a woman who's normal color vision and type AB blood. The woman's father had color blindness. And they tell us color blindness is determined by an X-linked gene, while blood type is determined by an autosomal gene. And you'll remember that blood type was an example of codominance, and so we have to remember that. So what I always like to do when I'm doing a problem like this is to go off to the side and write out what my symbols are going to be. And so since color blindness is a recessive X-linked gene, what I'll do is I'll say that X with a capital B is going to be normal vision, while X with a lowercase b is going to be color blindness. Remember, it's sort of convention in genetics that the symbol, the letter that you choose, has to do with the recessive or the mutant condition. So it doesn't matter what letters you pick, but the capital letter is going to be normal. The lowercase letter is going to be the condition, color blindness in this case. And then remember our blood typing, we have two dominant alleles. IA and IB are the dominant alleles, and then we have the recessive allele of lowercase I. So those are the symbols I'm going to use. When we look at this problem now, they ask us what are the genotypes of the man and the woman. Well, if we drew a little pedigree here, we have our man and woman, and we know in the previous generation her father was colorblind. So pedigree might look something like this. We're asking now about their offspring down here. We know that the man is colorblindness, so he must have an XY genotype that includes that colorblindness allele. We know the woman has color vision, normal color vision, so we know that she has a dominant allele. We don't know what her other X allele is. Except that we know her dad was colorblind. And so since her dad is colorblind and he could only have passed on to her the recessive, we know that this woman must be a heterozygote. That's why they gave us that information. Separate to that, we also have blood type information. So if the man is blood type O, that means he has two recessive alleles, lowercase ii. The woman has blood type AB, so she must have both dominant A and B. So that gets us through part A. What are the genotypes of the man and the woman? Now, what proportion of their children will have this, that, or the other thing? I want to point out the language here. What proportion of the children is asking us amongst all the children? We don't care about the sexes. Some of these questions will ask, what's the chance of having a boy that's affected in some way, or a girl that's affected in some way? In this case, they're asking us about children. So we're looking at the total offspring. So we have two choices. Basically, we have a cross that looks like this. We have the male that is type O blood and colorblind, crossed with a female who is type AB blood and has normal vision, but we know she's a heterozygote. She's a carrier for the colorblindness allele. We could do a dihybrid Punnett square, and that would be totally fine, especially simplified by the fact that the male only has one blood type available. So if we did that, we would go across like this, and it doesn't matter whether you put the male in the top or on the side, but I'm going to do it this way. The male can give two gametes here. It's going to be blood type O with the X chromosome, or blood type O with the Y chromosome. Those are the only two options we have here, so it makes our table a little bit easier to deal with. The woman, on the other hand, we have four possibilities, so we'll be systematic about it. A and dominant, A and recessive, B, oops, don't do that. Sorry, let's get rid of that. Don't mix up your symbols, everybody. So blood type B and dominant, or blood type B recessive. Okay, 4 possibilities. And just like we've seen in chapter 3 and so forth, we're going to fill in our little alleles from the top and the side. Okay, and this is just about being careful that you don't mix up your symbols, especially if, like I'm doing, you're making sure that you're putting your dominant alleles first. Sometimes it takes a little bit of thinking to make sure you do it right. All right, so dominant Y, IA, recessive, and Y, IB, I, dominant Y, and IB, I, recessive Y. Oops, and I did it again. Stamper, knock it off. That should have been one of those. Okay, so we've done that. Now we could have done 2 separate Punnett squares. That would have been totally fine. We could have done one with blood type, and we could have done a separate one with color blindness, and then combine the results together. Since this one was only 8 boxes, 8 possibilities, I decided to do it together. Frankly, if it had been 16, I probably would have done 2 separate ones, but you have a choice. So now we have to interpret what's going on in these cases. And so we can go through and say, all right, the top row, first box, we have blood type A, we have normal vision, and this is a female, right? The next box over, blood type A, colorblind, female. The next box, blood type B, normal vision, female, and blood type B, colorblind, female. Bottom, I get A, normal vision, male. Now it's got the Y chromosome. A, colorblind, male. B, normal vision, male, and type B, colorblind, male. Now we've done all the hard work. Now we just go back and answer the questions. So what proportion of the children will have color blindness and type B blood? Well, let's look for them. Colorblind and type B. I get 1 here, colorblind and type B, and I get 1 here, colorblind and type B. So 2 out of 8 gets me, 1/4. So I'd say 1/4 for that question. Now, if it asks what proportion were colorblind type B boys, that'd be 1 out of 8. Colorblind type B girls, 1 out of 8. But colorblind type B children, I'm going to combine those together. So I get 1 out of 4. 2 out of 8, 1 out of 4. What proportion will have color blindness and type A blood? Same question. I'm just looking for that in my table. I get colorblind type A here and here. So again, it's going to be 1 out of 4, or 2 out of 8. What proportion will be colorblind and type AB blood? There's no way I can get AB blood, right? From someone who's AB and someone else who is O. I can't get AB blood, so that right there is going to I get 0. Right. If I had done these as 2 separate Punnett squares, just so that you can see how that works, I would have set up one little Punnett square that looked like this with just blood type, and I would have spotted that I'm going to get 50-50 type A and type B blood. So 1/2 type A and 1/2 type B blood. And remember, in probability is a multiplier, I would have had the other little Punnett square that had to do with the color blindness situation. And I would have gotten my 4 possibilities here. Now, if I wanted to differentiate based on sex, I could, but this problem isn't asking me to, so I'm not going to bother. what I'll find is that the left column here is normal vision, and the right column over there is colorblind, half and half. And so then I get my questions up above. What proportion of the children will have color blindness and type B blood? Well, color blindness, if I switch to a thing here, color blindness was a 1/2, type B was a 1/2. That word and tells me I'm multiplying. So 1/2 times 1/2 gives me 1/4. And I'll do the same sort of a thing with any sort of other probabilities that I want to answer. So this is an example of X-linked inheritance. We want to just make sure that we're using the superscripts for those alleles. So X with the superscript for the allele, dominant or recessive, and Y typically doesn't have, there aren't many Y-linked genes. The book kind of asks about that. Why might there not be very many Y-linked genes? And you can think about that one as a separate issue. But for now, there's a walkthrough of problem 5.10. If you have any questions, let me know. Otherwise, keep up the great work. Good luck, and I'll talk to you again soon.